Hi everyone, and welcome to today's Chemistry Daily Booster. This is number 10 in our Paper 2 series, and this is advanced information listed topic for both the higher chemistry and foundation chemistry. When we talk about the rate of reaction, then what we're really discussing is a measure of how quickly our reactants are being used up or the products are being formed. And quite simply, if we want to actually just work out the rate of a reaction, all we do is the amount divided by the time, because that then gives us a numerical value about the rate of reaction that we can then compare under different conditions. What you'll find is there are two different ways that we generally record our reactions. Now, these are both to do with reactions where we're generating gas. Because this is listed as one of the assessed practical parts of your advanced information, then there is a good chance it could involve looking at these experiments. So we're going to look at the one on the left first of all. This is an upgrade from the simplistic way, I didn't even bother with a picture, counting bubbles. Because if we count bubbles, then yes, okay, we're going to have a number of bubbles in a given time, but those bubbles are going to have different volumes. So in terms of the accuracy of your results, it's not great. We can upgrade that slightly to the upturned measuring cylinder. So what we do is we fill the measuring cylinder full of water, and then you're going to turn it upside down in a tub of water, making sure you only move your hand away once it's underwater. We then connect the delivery tube to make sure it's underneath our measuring cylinder. As the gas is made, it displaces the water from the measuring cylinder. We read the volume. There are some problems. If that little delivery tube happens to slip, then we could lose bubbles of gas. You've also got to make sure that you don't have any air trapped in your measuring cylinder when you turn it upside down. So it needs to be completely filled with water, which isn't always the easiest thing to do. How can we make it even better? Quite simply, we use a gas syringe. So if they give you either counting bubbles or using an upturned measuring cylinder and ask you how you could improve the experiment, use a gas syringe is the simple answer that gets us the mark. As far as rates of reaction goes then, you could be asked to calculate the rate from a graph. Now this could obviously follow on from a plot a graph question, because we do know that 10% of all the marks on the chemistry paper will be maths based. So plotting a graph could be a nice 3 to 4 marks as a question itself. Don't forget, when we plot a graph, you need to make sure you've picked a suitable scale for both of your axes to ensure that more than half of that graph paper is filled both horizontally and vertically. Make sure that both of your axes are labelled with a title and the units. And then we're going to plot our points with a sharp pencil using nice neat crosses. Not weird little tiny dots that get lost on any lines of best fit. Use a nice neat little cross so that we can still see them later. Lines of best fit in science, remember, can be straight lines, can be curves. Look at the data. In this case, it's blatantly a curved line. If you were to try to plot a straight line through this, your line of best fit mark is not coming, because what we're going to end up doing is just having a bit of a line sticking off, ignoring about 3 points altogether. That's not a line of best fit. So it can be curved, can be straight. Look at your points, decide which is best. Now, when we actually need to calculate the rate then, what we're going to do is calculate the mean gradient. We will do this if the question asks us to calculate the rate across a certain time period. So in this example, it's between 60 and 90 seconds. So if we're asked to calculate the rate between 60 and 90 seconds, what we do is we're going to plot a little triangle on the graph. So find 60 seconds, find 90 seconds, and then you're going to draw your horizontal line between them. What we then do is you just draw the line up to the curve from your 90 seconds, and then what we can do is read off the values for volume. So what we then need to do is work out the change in volume and the change in time. So change in time, 90 minus 60 gives us 30 seconds. Change in volume in this case, 50 minus 38, 12 centimeters cubed. So to work out our rate, we just do 12 divided by 30. And that then gives us the rate for that particular reaction. If they're being a little bit meaner, they could ask you to calculate the rate at a specific point. So they would say, what is the rate at, and I think this is 75 seconds. So what is the rate of reaction at 75 seconds? To start, we have to draw a tangent to the curve. So get your ruler out, place it against the curve, and make sure that it's touching, obviously at point 75, and then just make sure that on each side it is roughly equal distances from the curve itself. Draw yourself a nice line there. Once you've done that, all you need to do is then complete your triangle. I would always suggest looking to find nice easy numbers to use, because you're going to have them if you've drawn a decent enough tangent. So then pick easy numbers to use. In this case, you can see that we used the seconds there. We did 120 because that was a lovely little point that we could use. 100 minus 20 gives us 80 seconds. Then we also work out our difference in volume. 55 minus 23 is 32. To calculate the rate then, 32 divided by 80. Stick it in your calculator, you've got your rate of reaction there. We need to be able to recall the different factors that affect the rate of reaction and explain how they do this. Let's start off with temperature then. If you increase the temperature, you increase the rate of reaction. The reason for that is, as we increase the temperature, particles gain kinetic energy and they're going to move faster. This means they are going to have more frequent successful collisions. This phrase here, more frequent successful collisions, must be in your answer, okay? There's two parts to it. More frequent, first of all, so that just means there are more collisions in any given minute of time. And the successful part just means that they have exceeded the activation energy. So remember when we've looked at our reaction profiles, that's a terrible reaction profile because it's a weird angle, but this point here, okay, that is the activation energy. So activation energy is the energy needed to start a reaction. The successful collisions are the ones that have exceeded that. The higher the temperature, the more likely they are to have successful collisions. So remember, temperature increases, rate of reaction increases, because the particles have gained kinetic energy, so they are moving faster and will have more frequent successful collisions. What we actually find then is that when we're considering the rate of reaction, it's going to be inversely proportional to the reaction time. So quite simply, 1 divided by time is directly proportional to the rate. If there are some bits from today's booster that you would like to go through in more detail, don't forget we have the videos on the main channel on the C5 playlist that you can use. You've also got your revision guides, and I do suggest having a look at some of those past exam papers just to get a bit of a feel for the kind of questions that can come up. And of course, don't forget to join us again tomorrow for our next daily booster.